Alessandro has the habilitation now.
Okay, good.
So he is the real director. In France, it works usually before you get your habilitation, you co-direct a PhD just to be sure that everything is fine. And during the PhD, usually you start to have the habilitation, the diploma that allow you to be a director. So Alessandro now is a formal director, and he has his own PhD student. But Marco is the first formal PhD student of Alessandro.
Okay, so last.
We started the stream on YouTube.
No, wait. Last point in the organization. I propose that after the end of the discussion question, we'll all disconnect from this Zoom. I will send you another link for the deliberation in order to have our Zoom for deliberation, and then connect back. This is the simplest because the streaming is already been set on this one.
Okay.
So I'm starting the record.
So, okay, I've also started the stream on YouTube, so it's going on.
Okay, so wait just a minute and then I'm done.
And 3 minutes left before 2 o'clock, so we should wait.
Yeah, we will wait 3 minutes.
How do I ask for permission to?
And it's supposed to be visible, is it?
Yeah.
Yes. I cannot. Marco, I think you should explicitly give me the permission to record.
Yes, yes, it is probably the case.
I think you can.
Permettre d'enregistrer.
Okay.
Now I think you should.
Yes, it started.
Okay.
It's good for me.
And we start right now.
We wait a minute and then we start.
Okay, I'm going to mute the microphone.
Same.
As a president, shall I introduce Marco right now? Okay. So good afternoon, everybody. It's my pleasure to introduce Marco Cavallone, who will present his PhD work during this meeting. The title is Application of Laser-Driven Particle Beams to Iris Rate Radiation Biology. The work which has been done at LOA under the direction of Alessandro Prato. So Marco, you've got right now almost 45 minutes to present your work.
Okay. Okay, so I will share my screen. Okay. Okay. So I will first thank everybody, all the people who are watching this presentation, and I also especially thank all the members of the jury and especially the reviewers for the time they spent on the thesis. So today I will present the subject of my thesis, which is the application of laser-driven particle beams to high-dose radiation biology. Okay. The aim of this thesis is to study how to use laser-driven particle sources for application to radiation biology. So I will start with an introduction to explain why and how laser-driven particles are interesting for medical applications. And then I will talk about the challenges related to the use of such beams in radiation biology experiments. So I will first present the techniques to deal with laser-driven protons that require special attention to shape the beam and adapt the dose distribution of the target. And then I will address the issues related to the dosimetry of such beams, and I will in particular focus on the use of ionization chambers. And finally, I will present two applications. So the design of a beamline for single-shot irradiation with a high-charge laser proton beam, and then the first radiobiology application of a kilohertz laser accelerated electron. So laser-driven particle sources have received great attention after the implementation of the chirp pulse amplification technique in the laser field. Such technique consists in stretching in time a short laser pulse by separation of its spectral components, which allows to amplify such pulse using more compact optics and enable the construction of tabletop lasers capable of reaching power up to the petawatt level in pulse duration ranging from picosecond to femtoseconds. And by focusing such a laser pulse on a micrometric spot, we can reach intensities higher than 10 to the 18 parts centimeter square. And this allows to create plasma in matter and accelerate electrons to relativistic energies in a very short distance. And in particular, electrons can be accelerated by focusing the laser on a gaseous target. So in this case, the laser electric field propagates through the formed underdense plasma and excites large amplitude plasma waves. And this creates a longitudinal traveling electric field in the wake of the laser beam. And if we properly trap electrons in the accelerated region of this field, they can be accelerated up to hundreds of MeV. And while on the contrary, protons can be accelerated by a quasi-static field created in an overdense plasma, and for this reason we use a solid thin target. And in this case, the laser only propagates in the very first sheath of the target, and proton acceleration is mediated by electrons that absorb the laser energy and propagate through the target up to its rear side. And this drives the expansion of a plasma and leads to the formation of an electron cloud in vacuum. And this electron cloud in turn sets a very high electric field due to the charge separation, and this accelerates ion and protons in a cone normal to the foil surface. The peculiar property of these particle beams is their temporal feature, as they keep in some way the short nature of the laser pulse that generated them. So they are accelerated in extremely short benches that have a duration from few femtosecond to nanosecond, and that are separated by a delay that is limited by the laser repetition rate, or in case of protons, by the time that is needed to refresh the target, since the target is destroyed at each iteration. Now, to understand why this aspect is relevant for biology applications, we need to open a parenthesis on radiotherapy. The principle of radiotherapy is to kill cancer cells by depositing energy with an ionizing radiation. And this energy deposition leads to damage to the DNA and other cellular components by direct ionization, or by chemical damages induced by reactive radicals that are created by ionization of other molecules. Now, the amount of damage depends to a first approximation to the energy delivered per unit mass, which is called dose and is expressed in gray. Now, when we irradiate a patient, the probability of control and reduce a tumor increases with the delivered dose. Here, the brown curve in the graph. However, there is a limit on the dose that we can deliver because of the damage on healthy tissues that are also damaged by radiation, and here is the green curve in the graph. Therefore, the therapeutic effect of our radiotherapy treatment reposes on the separation of these two curves, which allow to spare as much as possible the healthy tissues for the same effect on tumors. And now this separation today is done in many ways. The first approach is to optimize the geometrical aspects of the dose delivery. So to deliver a more conformal dose to the tumor and spare the healthy tissues by concentrating the dose. And for example, this is done by modulating the beam intensity while the beam is rotating around the patient. And also different radiations are used today in radiotherapy to target different types of tumors, since each radiation has a different physical interaction with matter, and this leads to a different energy deposition in depth, as you can see here from the graph. But the aspect that is probably the less explored until now, in terms of the effect that it has on the therapeutic effect, on the therapeutic index, is the temporal modality of dose delivery. So the way the dose is delivered in time. Now, when living matter is irradiated, there are different phenomena that take place over different time scales. The very first effect of energy deposition consists in the ionization or excitation of atoms and molecules, and this can lead to direct damage to the components of the DNA. And then in a second phase, the reactive radicals that are created, especially oxygen radicals, react between them and diffuse, and can also generate indirect damage to the cell components. And this phase can last up to a second after the energy deposition, after which all the biochemical and biological processes take place. And this includes all the mechanisms that the cells activate to repair or even induces that, up to long-term effects on tissues. Now, it is important to compare these timescales with the timescale of a radiotherapy treatment. A conventional accelerator employed in clinics for radiotherapy typically delivered dose with a dose rate of few gray minutes, and a patient is typically treated with many sessions of few gray that last few minutes. So the key aspect to bear in mind is that the energy deposition occurs concomitantly with all these phenomena up to the biological one. And also the advantage of fractionating the dose in many sessions reposes on phenomena taking place at biological timescales, and in particular on the greater ability of healthy cells to repair sublethal damages than tumor cells. So this process of fractionation spares in some way normal tissues relatively more than the tumor. But on the other hand, all the processes and effect related to a fast dose delivery, so the delivery of the dose with a very high dose rate and with a very short exposure time, still needs to be elucidated. And this is a very active domain of research, especially after the discovery of the flash effect in 2014. And it was shown that delivering the therapeutic dose in less than hundreds of milliseconds, and therefore at a dose rate higher than several tenths of gray second, significantly spares the healthy tissues while the effect on tumor is maintained. So in other words, applying the dose in a very short time and with a very high dose rate can increase the therapeutic effect of a treatment. And this effect, that is apparently in contrast with the conventional protocols that consist in extending the dose delivery over a long period, is due to the fact that the dose is applied in a time that is comparable with the time scale of chemical phenomena, and such as the radical diffusion time. Now, the flash effect has been proved on many animals, and it has also been used for the first human treatment in 2019. And most of the experiments were conducted with electron beam produced by modified LINAC that delivered the dose with many pulses, having a peak dose rate in the pulse around 10 to the 6 gray second, and a mean dose rate higher than several tenths of gray seconds. Now, what is the relative importance of these features, such as the dose, the average dose rate, the peak dose rate, or the total dose in the pulse, on triggering the flash effect is still debated. And it is clear that laser-driven particles may represent a unique tool for research on high dose rate and fast dose deposition, since, as I mentioned at the beginning, they have a very short duration, and may deliver a dose in a pulse that can reach even few gray in a single pulse. So this means that they can deliver a meaningful dose in a time that is shorter than the time scale of radical diffusion and reaction, and with a peak dose rate up to 10 to the 12 gray second that cannot be reached by any other accelerator. And therefore, this peculiar characteristic of laser particle beams motivate radiation biology studies to investigate what is the effect on this temporal feature on living matter. And now I want to show you some results that have been obtained with laser-accelerated protons during the SAPHIR project, since this was the starting point of this thesis. And I participated to these experiments. Now, in the SAPHIR beamline, we used a joule-class laser that delivered 3 joules at the target to produce proton bunches with a maximum cutoff energy of 7.5 MeV. The spectral components around 6 MeV were guided with a quadrupole system up to the sample, the biological sample that was placed in air after a minor window, and a transmission chamber that you can see here in this picture that was used for dosimetry. Now, here you can see the typical dose distribution that we obtained at the sample, and that was recorded on an image plate. And the dose that was delivered in the black rectangle, that was the rectangle where the biological analyses were performed, was around 0.07 gray in a single pulse, with a peak dose rate around 10 to the 8 gray second. Now, we show that varying the delay between pulses, although we applied the same total dose to the sample, has an effect on cell mortality. And you can see this in this graph where you can see the variation, the oscillation of the cell mortality as a function of the delay between pulses. So these results were very important because they showed for the first time that the temporal structure of laser-accelerated proton bunches has an effect on cell mortality, and point out that the effect related to such a temporal structure are still unknown, because the relative importance of the temporal parameter and also the physical effect, the physical reasons behind this effect still needs to be elucidated. Now, these experiments to which I participated at the beginning of my thesis allowed me to identify what are the critical aspects related to the use of such beam to radiation biology experiment. And these aspects in particular are related to the shaping of the beam, which is critical for protons, and to the dose delivery at the target. So the very first challenge is to deliver an homogeneous dose at the target. And as you can see in the SAPHIR beamline, this parameter could be improved, since the biological surface stayed in the 50% isodose. And the improvement of the dose deposition at the target require the ability to precisely simulate the beamline and to adapt the beamline configuration as a function of the dose deposition at the target. And the second challenge is related to the dosimetry of such particle beams, which is challenged by the very high instantaneous dose rate of such beams. And many conventional instruments, such as the ionization chambers, requires a careful characterization at such a high dose rate. So I will start with presenting my work on the techniques to shape laser-accelerated protons. Now, when designing a proton beamline, we need to deal with 2 peculiar characteristics of such proton sources. A large divergence at the source that can reach up to 20 degrees, and that is a function of the energy, and a broadband spectrum with a cutoff that can reach few MeV, and that depends on the laser energy. Now, this broadband spectrum might be an advantage in some cases, since we need a polychromatic spectrum to irradiate thick targets with an homogeneous dose in depth, because of the fact that protons feature depth dose deposition. However, this also means that the spectrum needs to be carefully tailored. So we have basically 3 main goals to achieve when we want to design a beamline. We need to select the desired spectral components of such a broadband spectrum. We need to transport as much charge as possible to the sample that is placed in air, and we need to spatially shape the beam to deliver an homogeneous dose at target. And in last year, several magnetic devices have been used to accomplish one or more of these tasks. Dipole magnets, for example, have been used to irradiate cells with a thin spectral bandwidth, so with a high precision on the proton energy reaching the sample, since the dipole enables the separation of the energy components along one axis. However, they can't ensure a high charge collection, and their use is limited to in vitro irradiation of 2D targets. So for this reason, focusing magnetic devices such as quadrupoles or solenoids have been used in last year, and in particular, I focus my research on the use of permanent magnet quadrupoles, since they offer a good flexibility in the spectral selection and they are quite easy to handle. Now, how does a quadrupole work? So a permanent quadrupole is composed by 4 magnets that are positioned in such a way that the magnetic field can focus charged particles over one direction and defocus them in the other direction. So we need at least a system of 2 quadrupoles with opposite focusing plane to focus a beam in both transverse direction. And in this picture, you can see the system of 4 quadrupoles that was used in the Sapphire beamline during the Sapphire experiments. And you can appreciate how this system was designed to focus the proton envelopes around 6 MeV. Now, the major issue, as I said, is to deliver an homogeneous dose over a sufficiently large surface for radiobiology analysis. So let's say about 1 centimeter square. And this requires the beam to be spread after the transport system. So here you can see the Sapphire beamline simulated in Jan4. And as you can appreciate, the quadrupoles can be used to focus a quite narrow spectrum to the sample, but controlling the dose distribution, or in other words, the beam transverse dimension is quite challenging. And indeed, in the Sapphire beamline, we have seen that the dose distribution was not homogeneous, and you can also appreciate in the results of the simulation. And this is because the transverse dimension is less sensitive to the quadrupole configuration, and therefore it is challenging to optimize both the spectrum that we focus at the target and the dose distribution with a quadrupole transport system alone. So we need another component. We need to add another component to the line to separate the spectral selection from the spatial shaping. And the approach that I used during this thesis is to couple the quadrupole system with a scattering system, which is also an approach that is used in conventional proton beamlines. And in this case, the simulation of, so I simulated both the transport and interaction with matter with a single tool, a Monte Carlo tool that is Gen4. And this is fundamental because it enables the optimization of the configuration of the quadrupole system and the scattering system directly as a function of the parameters at the biological target. So a possible simple technique to optimize the dose distribution consists in using a flat scattering system to spread the beam, which is a technique that is simple to implement experimentally because it does not require a particular technological effort in the production of a flat scattering system. However, the approach is not so efficient in terms of the charge transported to the sample, because the scattering system just spreads the beam until the desired flatness is reached, and this is done at the cost of loss of charge. So one of the aspects that I addressed during the thesis was to find more advanced approach to flatten the beam profile and improve the trade-off between the total charge that we collect on the biological surface and the dose homogeneity at the sample. And in particular, the idea that I explored consists in placing a scattering system that is properly designed inside the quadrupole transport system. So by placing this scattering system in the quadrupole transport system, not only we can play with the beam diffusion, but we can also actually intermingle the trajectories by introducing different energy losses on a plane perpendicular to the beam. So in such a way that we take advantage of the chromaticity of the following quadrupole, and we modify the beam profile at the sample. So you can get this idea by looking at the figure, at this figure, where you can appreciate how the introduction of an energy loss on an external trajectory of the same energetic components can mix the proton trajectories at a certain distance. But now the design of such such a scattering system is not straightforward, since the energy losses that we want to introduce, and therefore the shape of the scattering system, must be optimized to properly modulate a beam that has a polychromatic spectrum, and this spectrum also varies over the transverse section of the beam. And then we want to obtain precise parameters at a given distance from the quadrupole system. So I developed a genetic approach to optimize the design of this scattering system. And this approach consists in coupling Gen 4 simulations with a genetic algorithm that I developed to shape, to optimize the shape of this scattering system, that is composed by, as you can see here, many tiles of variable thicknesses. So here, each color is a different thickness. And I implemented a Gen 4 code to be able to simulate the effects of each thickness placed in a given position of the scattering system on the parameters at the target, such as the flux or dose maps or the spectrum. So in other words, with such a code, we can construct a database, and this database allows to recreate the output at the target for any given random scattering system, as shown here. And this database was used as input in a genetic algorithm that I developed, and that is described, the principle is described in the scheme below. So very briefly, genetic algorithms are techniques that have been developed to find the best solution or near best solution to optimization problems where we have numerous parameters to optimize, and therefore we cannot use an analytic approach. And very briefly, a population of possible solutions, so in this case, random scattering systems, evolves through an iterative process from a generation to the next by random recombination processes, such as it is the case in genetics. At each iteration, the best solutions are selected according to a fitness function that contains the parameters that we want to optimize and that guides the promotion of such a population of solution through the generations. So in our case, the scattering system is optimized using a fitness function that evaluates the parameters at the target, such as the total dose delivered or the homogeneity of the dose. Now, this approach was tested with the Sapphire transport beam line that I simulated in Gen 4, and I validated the simulation of the transport in Gen 4. And on the left, you can see the difference on the beam flux over a surface placed after the transport system. In case we use a flat scattering system or a scattering system that is designed with a genetic approach that I described. And as you can see, the beam is flattened more efficiently with this second approach. Or in other words, the beam is more homogeneous compared to the use of a scattering or of a flat scattering system for the same total charge collected on this surface. And with this approach, we can also shape the dose distribution on the target, which was the aim of this idea. And here you can see the difference in the dose distribution obtained at a target placed in air after a Miller window. In case we use a genetic approach, so a scattering system designed with a genetic approach, or a flat scattering system. So you can see that for the same maximum dose delivered on the target with such a scattering system designed by a genetic approach, we can flatten the beam more efficiently. So now, besides all the issues related to the proton transport and shaping, as I said, the other major issue that concerns laser-driven protons and also electrons is the dosimetry of such particle beams. Dosimetry at high dose rate is challenging because of the limitations of different detectors at high dose rate. And for dosimetry of flash beams or laser-driven particle beams, radiochromic film have been largely used as a dose reference because it has been demonstrated that they are dose weight independent up to 10 to the 12 gray second. Our radiochromic film consists in a micrometric films that contains a sensitive layer that changes the optical density after irradiation, as you can see in the picture. And by calibration, of the film response with a known source, we can relate the optical density to the dose absorbed by the film. And so although they have several advantages, such as the fact that they are dose rate independent and also that they provide spatial information on the dose distribution, the practical use of radiochromic film is not viable for long-run experiments, since the film cannot be reused again once it has been irradiated, and also it provides an indication of the delivered dose after 24 hours after irradiation. So there is a great effort to transfer ionization chamber to high-dose rate dosimetry protocols, since ionization chambers are the reference instrument for absolute dosimetry in clinics, and most of the dosimetry protocols in clinics are based on the use of ionization chambers. And so to understand the issues related to the use of ionization chamber in high-dose rate beams, we should quickly recap the working principle of an ionization chamber. So it consists in a gas volume, typically air at atmospheric pressure, that is ionized when radiation passes through this volume. And the negative and positive charges that are created by radiation are collected to the electrodes by applying a voltage, and the collected charge is then read by an electrometer connected to the chamber. Now, the charge can be then related to the absorbed dose by calibrating the chamber, so through the calibration coefficient n, and also through a series of factors that contains that accounts for different conditions between the calibration of the chamber and the condition at which the chamber is used, such as the beam quality or the temperature or pressure, and also the recombination. So the recombination factor is what causes the major problem at high-dose rate, because due to the high instantaneous density of the charges produced in the volume, the charges recombine and only a fraction of the charge is collected to the electrode. And this fraction of charge that is collected to the electrode is called ion collection efficiency, and is the ion inverse of the recombination factor, and is expressed as the ratio between the charge that is collected and the charge that would be collected if recombination is negligible, which is called saturation charge. Now, the major issue is that such a factor is not fixed, but it depends on many parameters, such as the geometry of the chamber and also the temporal feature of the dose delivery, such as the dose rate, the peak dose in the pulse, and the pulse duration. So we characterized, in collaboration with the EMNC laboratory, recombination in an EBA Rezo nanochamber, which is the smallest available chamber. It has an electrode spacing of 0.5 millimeter and a volume of 0.003 centimeter cubic. And here you can see a picture of the chamber. And the interest of having a very small volume is that recombination should be reduced because of the lower time spent by the charges in drifting towards the electrodes. And also the small volume is interesting for the transfer of ionization chamber to laser-driven particle dosimetry, since the fields in this case are typically small. The transverse dimension of the field is typically small, in the range from a few millimeters square to centimeters square. And an accurate dosimetry of a small beam requires a chamber that has a volume that is smaller than the beam section. So the chamber was characterized at the modified linac of the Schur Hospital of Lausanne, which is used for flash radiation therapy research. And the accelerator generates 5 MeV electrons, and is able to deliver a dose per pulse between 1 milligray and several tenths of gray, with pulse durations ranging from alpha microsecond to 3 microseconds. And here you can see the exit of the accelerator and the setup the experimental setup. So the chamber was inserted in a water equivalent phantom at 1.5 centimeter depth, and the dosimetry at each irradiation was performed with an EBT3 film that was placed on the phantom surface, as you can see in this picture. And you can also see here the typical dose distribution on the film for the shorter distance to the source. And the dose was evaluated in the ROE, in the small ROE of 5 millimeter diameter. Now, to investigate the chamber response in a wide range of dose per pulse, from about 10 milligray per pulse to 10 gray per pulse, we irradiated the chamber by placing the setup at 3 different source to surface distance, and we increased the voltage of the accelerator from 100 volt to 300 volts, which increased the accelerated charge. And we repeated this for 2 pulse durations to investigate the effect on the dose rate and of the dose rate and of the pulse duration on recombination. Now, the dose was measured. The dose that was measured with the film was corrected using 2 factors to obtain the dose as the Razor depth. And these 2 factors take into account the influence of the distance from the source on the dose ratio, and the influence of the grid tension, since the beam energy slightly decreases when passing from 100 volt to 300 volt of the accelerator grid. Now, I won't enter into details on these factors that we can discuss later. I will go directly to the results of the calibration. So we were able to obtain the calibration curve for the Razor that is shown here on the left figure, that shows the response of the chamber as in terms of collected charge as a function of the dose deposited in a pulse. And as you can see, the response is not linear, which reflects the fact that recombination increases with an increasing dose per pulse. And also the curve of the 1 microsecond duration lies well below the curve of the 3 microsecond duration, which indicates that recombination increases with an increasing dose rate, the dose being equal. Now, if we divide the measured charge by the saturation charge, which is the extrapolation of the blue curve in the figure, we obtained the ion collection efficiency as a function of the dose per pulse, that you can see here on the right figure. Now, it is interesting to compare the Razor behavior, so here the red and black curves, with the behavior of a larger chamber, such as the advanced Marcus chamber that is also used in clinics, and that has twice the Razor electrospacing. And this chamber was previously characterized also at the Oriatron by Peterson et al. In 2017. And the ion collection efficiency of this chamber is reported with the dotted curves in the figure. Now, as you can see, the small volume of the Razor chamber ensures a higher collection efficiency than the Marcus chamber, and this suggests that the chamber can also be used efficiently for dosimetry at several gray per pulse. And this can be explained by considering the small volume of the Razor, as I said, which will lead to a lower probability of recombination. But the Razor is more, as you can see from the separation of these 2 curves, the Razor seems to be more sensitive to the pulse duration for the same total dose compared to the Marcus chamber. And the sensitivity with the pulse duration can be explained by comparing the pulse duration used for the characterization with the charge collection time of the chambers. So if the pulse duration is far smaller than the ion collection time, we can consider then the pulse is instantaneous from the chamber point of view, and no matter what is the pulse duration, recombination should depend only on the dose delivered in the pulse. And this condition is in part met with the Marcus chamber, which has an ion collection time of 20 microseconds, whereas this is not the case for the Razor. That is a collection time around 5 microseconds that is comparable to the pulse duration. So in other words, to explain better, recombination is sensitive to an increase of the dose rate up to a cutoff duration, below which the only parameter that affects recombination is the dose per pulse. And this was quite well represented in a paper of Gotz et al. In 2017, where you can see recombination in a Marcus chamber for different dose in the pulse. Each curve is a different dose in the pulse as a function of the pulse duration. And as you can see, as the path duration is decreased, the recombination increases up to a point or up to a cutoff duration below which recombination becomes insensitive to a further decrease of the path duration. So these results on the Razor chambers and these considerations are quite interesting because they tell us that when we choose an ionization chamber for dosimetry at high dose rate, we should consider the trade-off between these two aspects. So either we want an ionization chamber that can efficiently measure high dose per pulse without completely saturating, and so in this case we will go for a smaller chamber such as the Razor chamber. Either we want a chamber that is not sensitive to the path duration below few microseconds, and in this case we will go for a larger chamber such as the Marcus or even bigger. And in this case, so this second choice would also make ease the transfer of such a chamber to dosimetry of laser-driven particles, since this means that the chamber could be calibrated at a modified linac, such as the Oretron, for example, and that the calibration curve obtained with microsecond path duration would be also valid for electron beam accelerated by lasers that have a much shorter path duration. Now I will present the application of two different laser-driven particle beams. Most of the radiation biology experiments with electrons and protons have been performed with Joule-class lasers running at 10 Hz. And in the following, I'll present two interesting alternatives to this type of laser. So protons accelerated by high-energy laser delivering hundreds of joules at the target and firing a shot every hour, and electrons accelerated by high repetition rate lasers that delivers few millijoules at the target. So let us start with the first option. So with a Joule-class laser, it is possible to accelerate nanocoulomb proton bunches, so typically delivering around 1 gray at the target, as we shown in the Zafir experiment. And this is interesting because the dose in the pulse is comparable with a typical dose fraction in conventional radiotherapy, but the dose is delivered in few nanoseconds with a dose rate up to 10 to the 8 gray second. But another interesting application of laser-driven protons is to reach flash-like conditions that are challenging to reach with conventional accelerators. And because of the limitation on the repetition rate of laser-accelerated protons, that is currently around 1 Hz, and which is limited by the time needed to refresh the target, a viable option to reach flash-like conditions is to go to multi-joule lasers that delivers hundreds of joules at the target. And with such a laser, it is possible to accelerate tens of nanocoulomb in a proton bunch. So more than 1 order of magnitude. So the charge is more than 1 order of magnitude higher than the charge accelerated by Joule-class lasers. So I designed the experiment that we will perform in December at the Lully laboratory with the Pico 2000 laser. And such laser delivers 100 joule at the target with pulses of 1 picosecond duration and fires a shot every hour and a half. So in the left figure, you can see the expected proton spectrum that was obtained using previous measurements with a film stack and with a film stack spectroscopy technique that I developed and validated during the thesis. And a total charge of around 57 nanocoulomb is accelerated, and with an energy cutoff higher than 12 MeV. So the charge, as I said, is more than 1 order of magnitude higher than the typical charge obtained with Joule-class laser, and the energy higher than 12 MeV would allow to irradiate thick targets up to 500 microns. And the goal of the experiment is, in fact, to irradiate with a single shot a thick target such as spheroids or in vivo zebrafish embryos using a field of a dimension of 5 by 5 millimeters square. And you can see on the top a scheme of the beamline design. And the approach that I used for the beamline design is the one that I presented previously. So coupling a quadruple transport system with a scattering system. And we will use a system of 4 quadrupoles with a gradient around 100 Tesla meter to transport the proton energies around 10 MeV. And you can see the envelopes of different proton energies along the transport system in the 2 figures. And focusing the components around 10 MeV will allow to irradiate up to 500 micron thick targets. And the biological sample will be placed in air after a Mylar window between 2 radiochromic films that will be used to perform dosimetry at each shot and also to infer information on the uniformity of the depth dose profile in the sample. And in fact, in case of volumetric irradiation, the shading of the proton beam is more complex than what I presented before, since we need to optimize not only the transverse dose homogeneity, but we need to also accurately shape the proton spectrum in order to reach a flat depth dose deposition. And this is possible by coupling the transport system with a flat scattering system, provided that the spectrum that is focused at the target with the transport system alone produces an increasing profile of the depth dose. So to explain better, you can see here in black the spectrum focused at the biological sample with no scattering system, and here in black you can see the corresponding depth dose profile in the sample. So in this case, if we use a flat scattering system of increasing thickness after the transport system, we can increase both the transverse and depth dose homogeneity, since such a scattering system shifts the spectrum towards lower energies, which also leads to a flattening of the depth dose profile, and moreover, it will spread the beam until the desired homogeneity, the desired transverse homogeneity is reached. And this is clear in this table, where you can see how the increasing thicknesses reduces both the depth error and the transverse error up to a point in which the depth dose profile is degraded. So in this case, at around 120 microns of the scattering system, which is due to the excessive energy loss, which inverts the trends of the depth dose profile. So with such a design, we expect to deliver a dose higher than 10 gray in a single shot, with an acceptable level of dose homogeneity, and we would reach a dose rate higher than 10 to the 9th gray second, so a very extreme irradiation condition. Then, as I said, the other interesting regime for radiobiology application is the use of high repetition rate electrons. So I will present the experiment that we performed at the 808. So a brief introduction before. Up to now, only Joule class lasers have been used for radiobiology experiments with electrons. So Joule class lasers running at 10 Hertz. And the advantage of such accelerators is that we can produce today high energy electrons up to a few hundreds of MeV, with typically charges of hundreds of picocoulomb and even up to 1 nanocoulomb in a single shot. So on one side, the interest towards such electron source is motivated by the high energy that already allows in vivo experiments. But on the other hand, the main limiting factor of this accelerator is the shot-to-shot instability, and in particular the pointing instability that is typically in the order of the beam divergence. So this means that the spot at the target can move of one spot dimension from shot to shot. So an interesting option to overcome the limit of the shot-to-shot instability is to use electron beams accelerated by kilohertz lasers, which have been recently developed. And so with such a laser, we can accelerate electrons up to few MeV. So the energy is limited because of the limited laser energy on the target. But the interest of using such electrons lies, as I said, in the high repetition rate, because it has the main advantage that we can average the shot-to-shot instability by integrating thousands of shots to reach the desired dose. And moreover, we can also increase the mean dose rate from 1 gray minute, that is typically the dose rate reached with Joule class lasers running at 10 Hertz, up to 1 gray second, as we will see in the following. Now, for the experiment, we used the electron beam produced by the Salmar laser system at the 808, And the aim was to characterize the electron beam from a dosimetric point of view, and to perform first irradiation of in vitro biological targets to validate the dosimetry and to study the effect of such beam on the biological response. Now, as you can see here in the picture, you can see the spectrum obtained in 4 consecutive days, which was quite reproducible from day to day. And as you can see, with this laser, we can accelerate up to 10 picocoulomb per shot of low energy electrons up to few MeV. Now the beam was let spread to reach the desired homogeneity at the target, and we inserted a vacuum tube to get closer to the source in air. And in this tube was inserted the entire irradiation side using a customized holder. And this holder contained the plastic support for the cells that you can see here in the picture, and dosimetry was performed at each shot by using an EBT3 film that was placed in front of the cells, and with the Rezo nanochamber that was inserted in the holder behind the cells. Now, to precisely measure the dose delivered to the cells, since the energy of the electrons is very low, we needed to quantify the decrease of the dose between the film placed in front of the cells and the cells. That is due to the plastic support of the cells that was around 800 micron thick, and the air gap. So we performed before each series a double film measurement, and you can see the setup in this picture. And in this measurement, we placed a film at the cell position and a film on the surface of the holder as it was performed during irradiation. And this measurement was performed to obtain the ratio between the 2 doses, so the factor R in the formula, to correct the dose measured by the film in the post-processing analysis and obtain the dose in the cells. Now, these measures was performed before each series, as I said, and here you can show you can see the results of the measurement performed in 4 different days. And so, as I said before, we can reach values of dose rate up to 1 gray second, so 1 order of magnitude higher than the gray minute reached with Joule class laser. And this measure was also performed to verify the beam alignment before starting an irradiation series, since we adjust since the irradiation site was fixed in the tube, so we were obliged to align the beam pointing at each irradiation. And once the beam was aligned, the dose distribution was stable during irradiations, as you can appreciate from the picture, where you see the dose distribution in 6 consecutive irradiation on the EBT3 film. And we managed to reach an homogeneous dose in the red spot, which was the area used for the analysis, in the range of ±7% in most of the irradiation. The major issue that we encountered in the experiment was the drift of the beam spectrum during irradiation. We observed, in fact, that in the post-processing analysis, that the ratio between the dose measured by the front film and the Razzo placed behind the cells drift as a function of the exposure time. And you can see it in this picture, where I show the typical drift between the 2 responses, so the response of the film and of the Razzo, during 3 different irradiation series where we perform a dose escalation. So we increase the irradiation time. And the fact that this ratio is drifting means that the spectrum is drifting, and also that the ratio used for the dosimetry, so the parameter R in the formula, is drifting. And therefore, the dosimetry was affected by uncertainty that in our case was, however, limited to 10%. And this drift was likely to be related to the opening of a shutter that we used to block the beam, and the shutter was placed in the laser chain before the last 4 optics. So the opening of the shutter might produce a transient thermal phenomena in the optics when it's open after it has been kept closed for the time needed to replace the sample. So this problem can be simply solved by placing the shutter right after the last optic of the laser chain. And with this electron beam, we performed our first survival assay on colorectal cancer cells, HCT116, which were grown both as monolayer and also in the spheroid configuration, which is interesting because the oxygen distribution in such sample reproduces more closely the oxygen distribution in tumors, in which the inner part is less oxygenated than the outer part, and therefore it is more radioresistant. And for both configurations, we irradiated the wild-type cell line and also the radioresistant counterpart, P53, in which the mutation of a tumor suppressor gene, the P53 gene, gives to such a cell line a higher radioresistance than the wild type. So here you can see the survival curves obtained for the monolayer configuration. And these results are in line with what we would expect from the experiment. So the survival curves have the typical shoulder shape of low LET radiation. And the more radioresistant cell line, the P53, lies well above the wild-type cell line. And moreover, we also found values of the dose generating 10% of survival that are close to typical values obtained with conventional sources of a comparable LET. And this is also in line with results reported in literature showing no difference in the ERB of laser-driven particles and conventional particles. So the results goes in the right direction and confirms the quality of the dosimetry. And then we also tried to explore the effect of a fractionated irradiation. So we irradiated the sample with the same total dose delivered with 5 trains of pulses, as you can see here in the scheme, that were separated by a variable delay of 30 seconds, 10 seconds, and 5 seconds. So similarly to what we performed in the Zafiro experiment with proton bunches. And as you can see, we detect no oscillation for the cell monolayers, while an oscillation of cell mortality seems to emerge from the spheroid samples. And this might be due to the fact that we delivered a too much high dose, which was around 6.5 gray, and this dose corresponds to a very low survival for the monolayers cells, around 5% survival. And this can flatten the curve and prevent an oscillation to emerge. This dose corresponds to a 10% survival for the spheroids, which are more radioresistant, as I said. And this might explain why we observe such an oscillation only in the spheroid samples. So these last preliminary results are quite promising, since they show again the interest of exploring the effect of the temporal modality of those delivered with such beams. And further experiments are certainly required to confirm these results and also to improve their accuracy. For example, by solving the dosimetry issues related to the drift of the spectrum during irradiations. So to conclude, the first important conclusion is that laser plasma accelerators are a very versatile tool, since they can produce both proton and electron beams with very peculiar characteristics and with an extremely high peak dose rate. So I presented some of the issues that are related to the use of such sources for radiation biology experiments. We have seen in particular that laser-accelerated protons require a careful spectral and spatial shaping because of the characteristics of the source and the dose deposition in that. And that the shaping of such beam can be performed by coupling permanent magnet quadrupoles with scattering system. And about that, I also presented the advantage of using a genetic approach that I developed. And then I discussed one of the other issues related to the use of laser-driven particle beam in radiation biology, which is the use of ionization chamber for dosimetry. And in particular, I presented the characterization of a red zone nanochamber. And the results are very interesting because they show that such a chamber can measure high dose per pulse, up to tens of gray per pulse, thanks to the small volume. But they also show that the chamber is more sensitive to the pulse duration. And these two aspects, as I discussed, must be taken into account when using an ionization chamber for dosimetry at high dose rate. And then we have seen the application of 2 attractive alternatives to the 2-class laser driven particles. And I presented the design of the beamline for the experiment that we will conduct in December at the Lully laboratory with a with a multi-joule Pico 2000 laser that can produce high charge per bunch. And with the setup that I show, we will able to deliver a dose, the therapeutic dose, in a single nanosecond pulse, and therefore with a dose weight higher than 10 to the 9 gray second. And then I presented the experiment conducted with kilohertz laser, kilohertz electrons at the SALMAR facility of the LOA. And the dosimetric characterization of such beam confirms the advantage of using such a beam for radiation biology application, because the dose distribution is quite stable thanks to the high dose weight. And also we can increase the mean dose rate up to 1 gray second. And to conclude, I would say that for the upcoming research in this field, very high energy electrons accelerated by Joule class lasers represent a very attractive option for the medical community, since the energy of such electrons already allow in vivo experiments, although very few experiments have been performed to date. And the very limiting factor, as I said, that should be solved is the shot-to-shot instability, and this probably requires a dedicated research on the source. And also a parallel research focused on boosting the charge per pulse of such beams up to few nanocoulomb would allow to increase the mean dose rate up to few gray seconds with such a source. Concerning the dosimetry, that we've seen that is one of the major issues, besides the characterization of ionization chambers, it is crucial to find other dosimetry systems for dosimetry protocols of such beam. And this is an issue that concerns also the community working on research on the flash effect. And therefore, a collaboration between the two communities would allow to test dosimetry instruments over a wide range of dose weight and define common protocols. But to perform all these studies and address all the issues that I've mentioned, it is fundamental to build facilities that are entirely dedicated to radiation biology applications, to be able to perform long-run experiments and also foster collaborations with the medical community. And this is mandatory to obtain robust radiobiology results and to perform also innovative experiments, and will also allow to dedicate the research on other related aspects, such as I said, the optimization of the source stability, the dosimetry protocols, and also the techniques to shape laser-accelerated protons in case of protons. Thank you very much for the attention.
Thank you very much for this nice talk. I start for questions, so I think I will ask to Raphaël Meucli, the top reviewer, who work at CHUV at Lausanne, to start maybe.
Yes, thank you. How much time do we have? just to know, is there something which is defined or not?
No, I don't think so.
So I guess that there are 2 rounds of questions or something like that. Is it? Yeah. Okay. So I will start with some of them. Just at the end of your presentation, you talked about 10% difference in stability, and you argued that it was due probably to an energy drift. But just before you mentioned that the homogeneity is plus or minus 7%. Don't you think that it is an easier explanation in general due to the shape of the beam, by the way, that the instability you may see in the biological experiments is more related to homogeneity than to anything else, in fact?
Well, I think this is a good observation, but if you compare, if you see the beam shape of all these points, the beam is really stable. So by analyzing the results, I couldn't see any link between a deviation of the beam pointing and this issue with dosimetry. So I think that really the issue is related to some thermal phenomena in the laser chain, and because you would need a
lot of difference in energy for ion chamber to have a difference in sensitivity and as well for the films. That's why I'm cautious with that. I would be cautious with that. But
well, of course, there might be an influence of the beam pointing, but not in the range plus minus 10%. With such an homogeneity on the beam shading.
Okay, I found you, of course, this is my field of interest, so I was interested by that part, but the description on the analysis of the sensitivity of the Razo chamber was quite interesting, but fundamentally I'm wondering something. We did, of course, the evaluation of the Marcus chamber, and we had 70% of correction. You have something which is about 40%, and I was wondering, when you go to the market and you want to buy 1 kilogram of carrots, and you put it on the balance, and the guy is telling you, oh no, this is not 1 kilo, this is 1.4 kilograms, so you have to pay for 1.4 kilograms. Well, I would be a bit surprised, and I would not be so much confident with the balance. So can you comment on that?
I think I didn't understand really exactly your question.
Okay, so
I mean, are you saying that it is not, this increase is not enough to justify?
It is a very high correction factor. This is 70% of the actual value. And can you trust a correction of 70% when you are at plus or minus 5%? You already have concerns, and you try to get sure that it is okay. You know, in medical physics, when you have a linac which is plus or minus 5%, you try to be sure that it is okay. So now we say, okay, just correct that value with 70% or 40%. This is I understand that you mean it's a big correction. Yes.
Well, I think we should check what is the error on this correction. So I think careful analysis on the error on the recombination correction is mandatory for to use this chamber with a small uncertainty on the dose given by the chamber.
Do you have an idea about that?
Well, in this case, we tried to analyze the error, and it was in the plus minus 5%. But the error on this recombination factor with such a technique, and of course, such a technique is also affected by errors on the dosimetry with the radiochromic films and the positioning of the films. So yes, I guess before using such a correction factor, we should be sure that it is correctly measured with an error lower than plus minus 5%. Because then the absolute value of the correction factor does not really bother us. I mean, the only thing that bothers us is a decrease of the sensitivity of the chamber when it goes to a really high saturation. In this case, we will be really bothered by the small sensitivity of the chamber.
If we had another online detector which would give us the information online, I just would say this is not a good tool to do the measurement. Don't you think?
Well, I think that we must explore other dosimetry tools. This is of course probably one of the main points that we need to explore for dosimetry, both in flash condition or with laser accelerated particles. As you know, it is a very active domain of research. So I think we have to find other online dosimetry instruments that do not require a correction at high dose rates, such as ionization chamber.
Okay, and now we have the order of magnitude of the beam of the beamlets or the pulses we have for where we have demonstrated the flash effect is about microseconds, and you have a beam which is of high interest because it is orders of magnitude smaller, so 5 picoseconds, things like that. However, we have no clue about if there's a flash effect there. And by the way, in general, we should talk about flash effect only when we have a demonstration of a biological effect. When we talk about physics, we should probably talk about high dose rate, and that's all, but not flash. But now it is in fact very interesting because there are these orders of magnitude difference in the pulse size, but this is an enormous amount. So do you think we could imagine to have something which is in between, or to modulate a bit the pulse size, so that we would have a range which would go from the microsecond to the picoseconds, but with different values in between?
Yeah, well, I think this would be something possible with proton accelerated electrons. So we should let them travel for a longer distance and let the paths spread in time. So I think we can play to a certain extent with the path duration, although it is certainly also linked with other aspects such as the spectrum that is focused. So it might be challenging to tailor both the path, the duration of the proton beam, and the spectrum that we focus on target. But I think that it's possible to make a drift from microsecond to nanosecond with a smooth path duration.
Okay, thank you.
Thank you.
Okay, thank you. So now I ask to Leonagiti, as the second reviewer, to make a comment maybe, who is head of ED laboratory in Pisa in Italy. So,
thank you so much. Thank you. Can you hear me? Yes. Thank you, Marco, for the nice presentation. I don't have many technical questions. I would just like to ask you some clarifications on some of the concepts and graphs that you have been showing. I would start from asking you, because this is something it's not my expertise. So I would like you to explain a little bit better this problem, this concept of oscillation of the cell survival with the delay between pulses.
Yeah. Okay, so to explore the oscillation of the cell mortality, what you do is just since the dose is applied by integrating a certain number of pulses, you just vary so you deliver always the same number of pulses, but you vary the delay between pulses for each sample that is irradiated. And you deliver the same dose that would be a dose that is not too high to cause all cells to die, and which is normally 10%, the dose that causes the 10% of survival. And then you can see according to as a function of the delay between the pulses, what is the survival fraction of the cells after irradiation.
And what does this observation tell you about the biology?
Well, this tells you if there is a variation of the radio sensitivity of the cells as a function of the way you apply the dose to the cell. So this tells us that when we perform experiment with such a sources, we also need to be careful with the delay we use for the. So we need to specify what is the temporal modality that we are using to irradiate such a cells. So this is something that is mandatory to explain, because as these results show us, the radio sensitivity of the cells is affected by the delay between the pulses.
So this means that if you do not observe oscillation, what is your conclusion when you do not observe oscillation?
Well, if we don't observe oscillation, the conclusion is that the response of the cells is not so the radio sensitivity of the cells is not affected by a variation of the delay, but then it doesn't tell us anything about the physics of the physical reason of the biological response. So it might tell us that this effect might be present at other past durations, or that simply the cell is not affected by such a phenomenon. Indeed, we showed in the Sapphire experiments, we showed that this phenomenon is related to the presence of a hard protein. So we know that the oscillation of the cells is related to the presence of a given protein, but still the variation of the radiosensitivity, so the physical reason of the variation of the radiosensitivity is still not clear.
Okay, so you have to design your radiobiology experiment taking into account this the presence of particular mechanisms, biological mechanisms that might be dependent or not, or you're probably looking for these particular mechanisms.
Yeah, I mean, you should look to it, but what I'm saying is that when you perform a radiobiology experiments, you should always you should always clarify what is the precise temporal feature of your beam, and this is something that is not always clear in the literature with laser-driven particles. So this might also explain why there are few differences in the results in this field.
Okay, sure. Another question is about the specific properties of laser-driven sources, and we know that they typically have a large energy spectrum, as you say it in your presentation, both in the protons and electrons. You probably discussed the potential and the possibility of using the energy spread in protons, enabling the longitudinal spread of the dose in the sample. I didn't catch any discussion about the energy spread in electron beams. How does that affect your measurements, and especially in view of the use of very high energy electrons, what do you expect is whether you expect this to be a limiting factor for the use of very energy electrons with large energy spread in vivo or in vitro?
Yeah, well, as you know, high energy electrons have a quite flat profile of the dose deposition. So of course the issue that we have with protons that are highly sensitive to the spectrum, I guess it has not the same impact in case of electrons. But of course, also in case of electrons, we need to tailor the spectrum if we want to reach a flat dose deposition. So it depends, of course, on the thickness of the target that you are considering. And I never deal with the design of a radiobiology experiment with high energy electrons. So I don't know in details the issue that we may encounter with such beams, but I guess that let's say the constraints are less strong than with laser accelerated protons.
And this was not an issue for your kilohertz experiments?
This was not an issue in the sense that we assume that in the 10 microns thickness of the cells, we consider a 2D radiation. So we don't consider the depth profile of the dose in the cells. We consider that it's just a monolayer in this case. Of course, with such an energy, if we want to irradiate a thick target with, for example, 5 MeV electrons, in this case, we should consider the spectrum of the beam.
Okay, then I have last question. It's more like a perspective question about the boost, as you say, the need to have a higher charge per pulse for the electron beams. and stability. From what you said, stability is more likely to be a technical issue, to be approached exploring the limitations of the actual beamline, if I understand correctly. So it's probably something that can be approached checking and carefully building your beamline, which is probably why I could agree in that. Although there are some intrinsic stability issues that might need to be addressed. For the charge, do you have any idea, any clue of how the charge per pulse could be increased?
Well, it's difficult for me to give an opinion on that because I never went deeply into the physical aspects of the interaction and production of electrons. So if you're asking me what are the physical mechanisms or that could be explored in the future to increase the charge per bunch, then I don't know how to answer to this question.
If you have been thinking about this, if you have been thinking about possible ways whether to enhance using pushing the production of a single pulse, or maybe using some clever way of double bucket, or
of course.
There are some ideas around. If you have, I just wanted to ask you to know from you whether you have been exploring this even from a general point.
Yeah, no, I've never explored this aspect, but of course one of the strategy would be to produce more interaction, more than one beam at the same time. So split the laser energy and produce more than one beam, and then try to refocus this beam. I mean, this is more a technical how to say option. But then how to improve the charge with a single interaction? This is really something that I cannot.
One final small question. This is probably a little bit more technical. In your kilohertz experiment, how was the gas production in the chamber being handled?
The gas was a nitrogen gas, and we could vary the pressure of the gas.
Was it a cell? Was it a gas cell? Or
it was just nitrogen molecules. It was not. Sorry, I mean I understand what you mean. It was a jet. It was a jet.
So
we could control the density of the gas and tune the electron spectrum. So another possibility that we had during the experiment was to obtain a more peaked spectrum at few MeV, for example, by decreasing the density of the gas jet. But we choose to have such an exponential spectrum that you saw in the image, because in this case, so with a higher density of the gas, because in this case we had a much higher charge, and this was also an important parameter because we wanted to play with the fractionation, and we needed to have at least one gray second. So this is why we chose to optimize the condition with the gas jet and use such an exponential spectrum.
Okay, that's all. Thank you very much.
Thank you.
Okay, thank you very much. So now it's time for Ludovic Donardi, with the medical physicist, work at the Institute Curie Orsay, to speak with me. Ludovic?
Okay, thank you. First, Marco, and as well, I would like to thank you for the invitation to the PhD defense. So, I found it was really interesting, as well as the reading of a manuscript that was really with many fields that were described.
also the application of laser to biology is really a vast and complicated topic. So you did multiple efforts to explain your work in many fields, multiple fields as varied as radiobiology, dosimetry of ionizing radiation, simulations, experimentations with various type of lasers. So we did a great effort in a very rigorous way. And also, sometimes the results are not so positive, for example, with W fractionation effect. But I think it's a remarkable achievement to obtain results with laser beams, and I know it because I also try to reproduce this effect with Mr. Cavallone, electron beams, so I know it's really how much it is difficult, and it requires extreme accuracy all the aspects of experimentation. So I have a few questions, for example, about the fractionation effect and W effect. It has nothing to do with the flash effect. It was demonstrated only in cells and in vivo, but not in vivo. So this fraction effect demonstrated in vivo, and how it be done, and what would be the interest, and which have clinical implications.
Well, yes, as you said, the only demonstration of the WV effect has been only in vitro, and yeah, it would be really interesting to see if this effect is still present in vivo experiments. And so I think this is something that would give us quite interesting information on the on the modality of the dose delivery that we can use in future radiotherapy protocols, since actually it tells us, at least in vitro, it tells us that the radio sensitivity of the cells is changing according to the way we deliver the dose in time. So then we know that the difference between an in vitro experiment and in vivo experiment is quite large. So I think it's mandatory before concluding anything about the therapeutic potential of this, and eventually a therapeutic potential of changing the delay between the pulses. It is mandatory to explore if this effect is still present in vivo, and then I don't know what could be exactly the let's say the biological endpoints that could tell us whether this effect is present or not. This is not my field, but yeah, I think this would be really, it's mandatory.
Okay, because for example, you said you didn't reproduce the effect with cells because you used a dose that was too high, so cell survival was too low.
Yeah.
But I mean, for all experiments, we have these cell survivors and these points at low survival. So would that mean these points could be considered as independent of the effect?
Yeah. Well, I think this is a question. I mean, I don't know if this effect could be dependent on the percentage of cell survival. So I guess this is another parameter that we should take into account and in such experiments.
One question about the radiochromic films you were using. So you use it for many applications and also various type of particles. So we know in clinics the use of radiochromic films is quite difficult because there are a lot of uncertainties. So we discuss it a little bit, but maybe I missed it. Was there an effect for the proton beam, an energy-dependent effect of the films and the
the quenching effect. And did you correct for this effect if it was?
Yeah, of course. As you said, the use of radiochromic films, especially with protons at low energies, is affected by the quenching effect around the Bragg peak. No, I didn't correct because I used the radiochromic films for mainly two reasons: to characterize the proton source and then to perform dosimetry on the sample. And for the characterization of the proton source, as you may have read in the thesis, I've just used a generic calibration of the films, which gives us information on the shape of the spectrum, but of course the total charge that we obtain is affected by an error that is also due to the quenching effect. And then in case of the dosimetry with radiochromic films, as you said, we should calibrate the films with low energy protons. For example, in the case of the Lully experiment, if we want to use radiochromic films for absolute dosimetry, it's mandatory to obtain to verify the response of the radiochromic films with low energy protons.
Okay, but we need these calibrations for many low energies since the laser spectrum are okay. Yeah,
this is true. We should obtain, let's say, the behavior of the film response as a function of the proton energy if we want to perform a very precise dosimetry.
Okay. This would be feasible. I mean, to obtain the dose with this calibration.
Sorry, could you repeat this?
This could be feasible if we had this energy calibration to obtain go back to the dose.
Yeah, I think this calibration will tell us what is the correction that we should apply to the film to obtain the dose absorbed by the film. So I think it's possible. Then I've never looked into the problem of correcting the quenching effect, but I know that there are techniques to correct for this effect with radiochromic films.
So about the dosimetry with laser, I wonder if...
Sorry, I just interrupt you a second because Alessandro is not here anymore and he's asking me to let him enter. Okay.
And I think Victor has some problems as well, connection problems, so I don't know.
It's okay for me at least.
Okay.
Alessandro is not here.
Victor, maybe. So we should wait a few seconds.
Yeah.
We have lost the two directors.
Participant 8. Okay. So, okay, Victor is here.
I just come back. I'm sorry, I have been disconnected 3 times this last 5 minutes.
Alessandro is trying to join, but
Leo is coming back.
Oh, okay.
So I don't know the reason, but this last 5 minutes I lose you for 3 times. I hope it will be okay. So I'm sorry I didn't.
No, don't worry. I think Alessandro has the same problem because.
And we're not on the same place. We used to work together. Perhaps there is a memory somewhere.
water memory or something like that.
A memory that old cold years. Okay, Alessandro.
Oh,
Okay.
Okay. Can we keep
Ale,
oui, je suis là.
maybe you should restart the recording. Is it
You need to give me permission.
again? Okay.
Sorry, it froze.
Participant. Okay, you should have the permission now.
Okay, so I'm sorry. Did I miss so much?
I don't know.
We won't tell you.
Oh, please.
so Ludovic, do you want to keep asking questions?
Yes, just I have a question about I was curious about the nano-rhythm. Do you observe the stem effect or differences between when the chamber was using axial or radial orientation?
We didn't check this aspect.
Also, do you think there is we can are you able to quantify the trade-off between the size of a chamber in order to this ionization chamber to be independent of the pulse duration? The accuracy we could achieve with really small ionization chamber because the smaller they are, the more we have noise measurements, for example.
Sorry, could you repeat, please?
Do you think we could decrease even more the size of the ionization chamber for them to be independent of the pulse duration? Or do you think this type of chamber again cannot be used for those rates because they will be too noisy?
Yeah, okay, I understand. Well, of course, I guess if we continue reducing the volume, then the sensitivity of the chamber and the noise will get higher and higher. I mean, it depends on what is the objective of the dosimetry. I think a chamber such as the Razor has already the possibility of measuring several tenths of gray in a single pulse. So I think the question is more if we accept that there is a sensitivity on the pulse duration or not. But then, of course, these are issues of the ionization chamber that should be solved probably by looking at other instruments such as scintillators or other online dosimetry.
But if I may, this is a really a good question, and this would be very interesting to solve the problem analytically, because there's a relationship between the response time and between the volume with the size of the pulse. So this could be quite not a simple exercise, but something which could be done quite easily, and we would know the different trade-offs, and that would be very, very useful for the users. So that's really interesting.
Yeah, of course. These are the two parameters that would that should guide us in the choice of a chamber. It depends on what we want to do with such a chamber.
Okay, I have a last small question regarding the field size we could obtain with laser driven beams. Do you think we could achieve a larger field size, for example, by scanning the beam? Would it be possible because if we use a scatterer, because of the beam properties, it would be possible?
Yeah, I think it's with a scattering system. Of course, you can reach higher fields, but larger fields, but with limitations on the spectrum, on the thickness of the field. So, as you say, one technique could be to scan the biological targets to obtain larger fields, and I think that this can be an option with laser accelerated protons. I know that there are some studies that deal with the techniques to scan biological target with laser-driven protons. So I think it's something that can be feasible and that can be done.
Okay, David, you've finished? Okay. So, Victor, I think it's time for you, as a former director of Marco Cavallone, if you want to take...
Okay, you catch me just at the moment of I have an important phone call. So, of course, first, I thank you for inviting me to be a part of your PhD jury defense. I will not tell about the condition when you arrive to the lab, and I think that Alessandro will detail the condition and all the difficulties and problems that you have to solve, and because it was a quite important time in the lab when you arrive. What I want to say is that I am extremely happy, extremely impressed, both by the quality of the result that you managed to have, the quality of the PhD thesis, the manuscript that I have the pleasure to read. It's very detailed, and you perfectly introduce the different tools that you need for your thesis. And also, I think it will be a reference thesis for many new PhD students, because you give the right level of details and of synthesis for understanding what we can do with laser plasma accelerator in their promise for use for radiobiology studies. So I've been very excited by when reading the thesis. Of course, your presentation even reflects the quality of the manuscript, and it's always a pleasure to discuss with you. And it was a pleasure when I was at École Polytechnique, but here now listening to your presentation and the achievement, it has been very nice to see where you are now. So and now I have a few comments about the manuscript, and then after I will go to a few questions. So the first one is you chose to call the particle beam that are produced by laser accelerated electron or laser accelerated proton. So I think that this terminology is quite confusing, because the laser is not accelerating in our experiment the electrons, and for sure not accelerating the proton. It's the plasma that accelerates the electron and the proton. So I think that it will be more correct to use the terminology laser plasma accelerated electron or laser plasma accelerated proton. So it can be LAPE, because we know that we can accelerate electron with laser, for example, vacuum acceleration. But this is it's another topic. It's not the way that we are using. So I think you have to change this abbreviation to reflect the physical process. Then after, I have a question. This was my main comment. Another comment is you define the dose, and I think it will be nice if you can put analytical formula, very simple case, that allows someone that doesn't want to use a sophisticated code to estimate the dose. For example, it's very easy when you have a particle with a mimicry path that is larger than a sample to estimate the dose. And you just need to put the value of the stopping power, and you can estimate analytically. And I think it's important to feel these quantities in the case of solid or in the case of gas. Or in the case of liquid, and in the case of gas. So I think it would be nice if you can add 3 cases, very high energy electron in water or in air, for example. It's instructive, and I always do this exercise when I want to explain and to transmit a message, and also to prepare an experiment is very important to have this number. So that is missing. That they can be. This I'm sure you can improve. I will send you the list of comments and the small typo that are still there, but it's very minor. Okay, so regarding the question, at the end you mentioned that the beam need to be monoenergetic for very high energy electrons, and it's not really the case for radiobiological need. Because very high energy electron, as you explained, and it's part also of the answer to the question of Leo, that you can use a big volumetric biological sample, and it will be uniformly irradiated. And even if the beam change in energy, it not affected those depositions. So I think that in this respect, very high energy electron, they offer more flexibility and perhaps less uncertainties than other particles. So that's something that I think it's not on the manuscript, but it was on your presentation. And we can have with monoenergetic electron a broad spectra with, for example, ionizing injection scheme that allow to produce a nanocoulomb charge in one shot. Even more. So there are a lot of room for. So the question that I wanted to ask you is, you know, at the end, I think it was one of the last slides, when you compare the temporal this oscillation feature in the monolayer, you don't find this oscillation in the monolayer with the kilohertz high energy electrons, and whereas we found in the monolayer this oscillation with proton. So you discuss the difference within the electrons between this observation with spheroid and with the monolayer, but you didn't discuss why this oscillation with monolayer disappear when you change from proton to electrons. So what is the reason? Is the level of dose that is different in the two cases?
No, I would just say that we cannot really conclude on these results. I mean, we didn't have a very fine control on the dose that we were delivering, and therefore, in this case, as I said during the presentation, we delivered a dose that was around 5% of survival. And so I think that before concluding that there is no oscillation of the cell mortality for monolayers, we need to perform other experiments and be more precise on the dose that we are delivering, because of the drift of the spectrum that we had during the irradiations. This also had an uncertainty on the dosimetry, and this prevented us to deliver the target dose. So sometimes we deliver 6 gray, sometimes 6.5. So I think this also affects the quality of these results. And so I just want to present because I think that there is something interesting showing that something is happening, but I wouldn't conclude on these results that there is no oscillation for electrons.
And I have a general question. You have been working with accelerator, with laser physicists, with medical physicists, with biology. What do you learn? What did you learn by working with all these different people with different mentality? And I have seen in the question that the sensibility and the way we approach a science problem is very instructive. So I wanted to have your opinion and your.
Yeah, well, I think I work with people from very different fields, and I think especially the difference between the physics, let's say the physics of particle acceleration, and then the medical physics is quite large, because I mean, for a medical physicist, if he looks at the results that we obtain in terms of stability, he would say that is really a poor stability. While for me, for example, comparing to the stability that we normally get, for me is very good. So I think, of course, there are two communities that have different constraints and different objectives. Often the community of laser particle acceleration is more focused on properties of the beam that are not really important. For example, in the case of radiotherapy, such as increasing the energy or increasing the collimation of the beam. So I think that there are different, let's say, different parameters that are taken into account. And yes, I've learned a lot, especially in working with people from the medical physics, because this is a field that I had never looked into before. So I learned a lot about the constraints that exist in this field, and what are the standard that we can reach, we should reach with laser-driven particles to attract this community.
Okay, so again, I would like to thank you for your very nice achievement, and perhaps can I ask you, where are you going to? What are the plans? Because you mentioned an experiment at Uli in December. It's ready. It will be delayed. What are you doing after that?
Yeah. The experiment at the Uli is is ready and will be performed. But I will start a postdoc at the Centre de Proton-Thérapie, so on the proton mini beam radiation therapy.
Okay, great.
And the team of the CPO is also collaborating with us in the experiment, so I will partly join the experiment as a member of the CPO. And
so this is as a postdoc.
Yeah.
Okay. So and then after you know that you are welcome at Weizmann as a postdoc if you want.
Thanks.
So again, I wish you the best, and see you soon.
Thank you, Victor.
I'm finished, Sandrine.
Okay, thank you, Victor. So Alessandro, thank you. It's time for you, director, to do 2 words about your PhD.
Thank you, Sandrine. So first of all, I would like to stress how much I appreciated working with Marco these 3 years. Marco, since the beginning, it happened to me to read a few weeks ago the presentation letter I got from his master thesis supervisor, and I really found out all he said about him. He's been precise. He's been performing a really high quality work. He's been creative. He's been independent, which is something we appreciate never too much in a PhD student. And it has been really trustworthy. We could give him things to do and be sure that he delivers what he promises. Marco's thesis started as complicated, being at the crossroads between different topics, being at a bridge between communities, and it got even more complicated in a way we couldn't foresee because of the cancellation of the Phoenix project. So Marco's thesis came in the wave of Saphir. So the very first experiment performed with the laser-driven particles in the field of biology, that was a really preliminary exploration. So once we wanted to go a bit deeper in the thing and build the experimental facility to explore this bridging between communities, the project was cancelled in a way that really could not be foreseen. This was very hard for us, and it was even harder for Marco. It's a very hard kick on your motivation knowing that the main topic of your thesis gets cancelled from one day to the other. I'm particularly proud of Marco being able to kick back, to go beyond this stop, and to keep working in the direction that it turned out to be the relevant one, to keep proposing experiments and activities. Experiments, half of them got cancelled due to coronavirus, which came right after, and which obliterated an entire year of thesis. But still, I'm very happy to acknowledge that his thesis will be used as a reference for quite a few theses to come. Now that experiments will start again on the topic, all the studies performed in bridging from laser plasma acceleration to radiation biology, to what's relevant and what's to be done, will be really of use. So particularly thank the reviewers who had to read 200 pages, but that's most interesting and useful for us. So I just conclude by thanking Marco again for this collaboration and to wish him the brightest future and possibly to come say hello when time be.
Thank you.
Okay, thank you, Alessandro. I will join Victor and Alessandro to tell you that it was really a great manuscript, and it will be for sure a reference for the future students. There is really a strong work on the bibliography, on the main experiment, on part of the experiments that have been done, applications, with laser-driven particle sources. So there's not a lot of experiments, so really you made a good job. And congratulations for this, for the presentation as well. That's very clear. I have just a small remark on the manuscript. There are plenty of abbreviations in it, and it would be helpful maybe to add a small lexical at the end, just to help the lecture, the people who want to read it easily. So I have a few questions to have. And first of all, maybe about the optimization of the transport line coupled with the scattering system. I don't know anything about genetic algorithm, and I just have an easy question. How long does it take from the input parameter to put in the algorithm to get the optimization of the scattering system? Is it really a long process, or is it just very short? If you are also you have the answer.
No, I mean the long part is just the Monte Carlo simulation that are used to produce the library, and that is used as input in the genetic algorithm. So, for example, to run a simulation with 10 to the 8 particle, it took for me with my computer power a few hours. And then once all the simulations, so you need to repeat the simulation for all the thicknesses that you want to explore the effect of, and then the genetic algorithm takes a few minutes. So once the library is obtained, then you can run the genetic algorithms many times to see what to tailor the parameter at the sample.
Another question about the transport system for frontal source. Yeah. I was not familiar with the transmission numbers, and I've seen from your thesis that it's close to 10-15% maximum, or even less. Is there any way to optimize the transmission and compare the transmission for LOA system to the transmission for ELIL experiment? And you said that from ELIL, the divergence of the source might be smaller, so the transmission should be better. Is there another way to optimize the transmission of such transport line?
Yeah, well,
which parameters can we play?
Yeah, well, as you said, the transmission that I typically get with a quadrupole system are in the percent range. and it is strongly affected by the divergence, the initial divergence of the beam. So in the study that I showed in the thesis for the Ellil beamline, for example, the fact that we have a very small divergence, this increased the collection efficiency of the system. Then, of course, to improve this number, we can also play with other transport systems, such as a solenoid, for example. There are other teams that use solenoid to focus the beam, and, for example, putting a solenoid before a quadrupole transport system might increase the efficiency, because the loss of charge in a quadrupole system is mainly due to the loss in the first quadrupole, and so putting a solenoid that focuses on both directions at the beginning of a beamline, this could also improve the efficiency.
And would it be possible to curve the target to focus the protons, maybe?
Yeah, I think this is something to explore. I don't know if there has been some work on that to optimize the source. Of course, one of the parameters we can play on is the divergence of the source. So if we find any strategy to obtain a more collimated proton beam, this would increase the collection efficiency of the system.
What is the maximum transmission efficiency that you can expect?
The maximum I got is 5% in the case of the Ellil facility. While in the Saphir beamline, we were more around 1% of the total charge that was transported in the. But when I say 1%, I mean the percentage of the total charge that is emitted at the proton source. So it depends if you mean the efficiency on a single energy component or the efficiency or on the total charge.
I've seen 15%, I guess, around 4 or 5 MeV on Pomarel's where the previous PhD studio, something like that, but maybe it's insane.
I think it was even higher than that. I don't remember, but for the single energetic components, we can also reach several tenths of % of efficiency.
So you had the opportunity to work with both laser plasma accelerators with electrons and proton source as well. So what would you push in terms of source, laser-driven particle sources? Would you push electrons or would you push protons and why? For application.
Yeah, I think probably for the interest of the community now in very high energetic electrons, I would push on electrons. Also because we can play with the repetition rate, and we can also go to high repetition rate electrons. But I mean, also protons with the oncoming petawatt laser, we will be able to reach several MeV at the source. So I think that also the continue on exploring the radiobiological effect of laser accelerated proton is something that we should explore.
Okay, I've got a question about the petawatt laser impact or energetic laser. You never mentioned the secondary particle emission or radiation emitted by the plasma when you interact with a laser, solid target or a gaseous target. You can have predatory radiation, for example, in the case of laser plasma accelerators, tools. Is there any impact on the biological cells that you put in front of the particle beam? Or did you avoid the effect by? I've not seen any deviation of the laser electron beam. So what do you think might be difficult for in vivo irradiation or even in vitro?
Yeah, I think this is a good observation, and we should really define what is the amount of radiation, especially with electrons. As you see, we didn't use any transport system. So of course, in this case, the sample is reached by all the radiation that is emitted by the interaction. So we should verify whether this percentage is important or not. When we look at the radiochromic film and we analyze the background, we see that this impact is not so relevant. But I never analyzed this aspect in details. So of course, in this case, a transport system would of course be suitable to separate the components.
Did you have the opportunity to put some control samples around the lot of axis regarding to electron protons to see if it was damaged by the just ambient environment, and to be sure that there is no contribution on the cell dying just due to the environment, which is not good for biological experiment?
Yeah, no, we didn't do that, but yeah, I think it's a very good observation. It could be one quick verification to perform to evaluate the amount of background.
Okay, thank you very much. I think I've
Thank
finished.
you.
So now it's time maybe to stop the Zoom meeting and to just have discussion with the other members of the jury. And we'll see after a few minutes.
Okay.
Did you already send the message, the link?
No, I'm gonna send it right now because I need to disconnect before.
Okay, so I will remain in this meeting. I will and I will send you the files for the rapport and for the delegation. Okay.
So we leave this room, is it?
Yes.
Yeah.
And we connect to the link that Alessandro will send just in a few minutes.
Okay.
Okay. See you.
Allora, no, c'è la diretta che va avanti. So we will leave the direct goes on, so you can stay connect. There are also people that are not that don't speak Italian. So stay connect if you want to see the proclamation.
Sì, capo, siamo in diretta, rimani collegata perché si stanno terminando per fare la preparazione di 10 minuti. La proclamazione, lo proclama il dottore, ora sono riuniti in un'altra riunione e poi tornano su questa che tu puoi vedere e lo proclama il dottore. Esatto. Dai, per favore.
So for all of you that are still on the YouTube direct stream, I think in few minutes they will connect again, and then there will be the proclamation. So stay tuned. Hello.
Ça va, il fait quel temps en Suisse?
Je sais pas, il fait bientôt nuit. Il tombait des halbardes pendant la nuit. J'ai commencé à faire froid.
Hein?
Ah oui.
Alors Marco, il est là?
Ouais, je suis là, ouais. Je suis bien là.
Attends, c'est pas enregistré, rassure-moi.
Ah non, je peux pas. Hein.
Pardon?
Est-ce qu'on a besoin d'enregistrer? Do we need to register?
Well, the stream on YouTube is working fine. So.
No, but now, do we need to register?
Probably
Record?
for formal reasons, yeah, probably. Okay, let's record.
Okay. But we cannot do any more jokes.
Tu donnes la permission, Marco?
Oui.
Le directeur de thèse qui demande la permission à son étudiant. Il est carrément vraiment indépendant, hein. C'est toi qui l'es plus.
So I think I will do in French, it will be easier for me. Donc Marco Cavallone, donc le jury est unanime pour te dire que le travail est fantastique. La présentation était parfaite, très complète, et tu fais finalement le lien entre plusieurs communautés, donc ça c'est un travail extraordinaire. Le manuscrit d'une très grande qualité également. Tu as collaboré avec beaucoup de personnes, donc voilà, tout le monde est unanime pour te féliciter pour ton travail et te décerne donc le diplôme de docteur de l'Institut Polytechnique de Paris avec les félicitations du jury. Donc bravo et bonne continuation à toi.
Félicitations, bravo.
Bravo encore. Et merci pour tout votre travail.
Merci.
Bravo, Marco.
Je voudrais prendre juste 2 minutes pour remercier des personnes. Donc bon, je le fais en français, c'est mieux pour moi. Vous m'entendez?
Oui.
Ok. Je voudrais d'abord remercier le LOA. Ça a été vraiment un laboratoire magnifique où je me suis trouvé très bien et je remercie vraiment tout le laboratoire, tous les gens qui ont collaboré avec moi et en particulier, je voudrais remercier le team de la salle noire pour la manip électron. Après, je voudrais remercier aussi, I would like to thank the CNR of Pisa for the possibility of giving me the possibility of performing experiments in their facility. Après, je voudrais remercier le CHU de Lausanne pour m'avoir donné la possibilité de faire des manips chez eux sur la dosimétrie Razor. Et après, en particulier, je voudrais remercier des personnes, Dario, Joe et Alberto Fazzi de Milan, qui ont collaboré avec moi. Et, so thank you Dario, thank you Alberto for the work we've done together. It's been a pleasure. Je remercie aussi Rachel Delorme parce que c'était vraiment magnifique de travailler avec elle sur la Razor. Et bon, finalement, j'ai fait une liste parce que sinon j'oublie. Finalement, je remercie Victor pour m'avoir accueilli dans le labo, pour le support qu'il m'a donné pendant la thèse, même s'il était loin, au final. Je voudrais remercier Émilie, notre biologiste, pour toutes les manips qu'on a fait ensemble, pour le support qu'elle m'a donné pendant la thèse. Elle a été très proche de de nous pendant cette thèse. Je sais qu'elle a partagé avec moi aussi cette aventure et je la remercie pour le support qu'elle m'a donné. Vraiment, ça a été un plaisir et j'ai appris plein de choses avec elle. Et au final, je voudrais remercier Alessandro. Vraiment, je pense qu'il mérite un remerciement spécial parce que il a été un guide parfait, non seulement d'un point de vue professionnel, mais vraiment, je crois que le rencontrer pendant ma carrière, pour moi, c'était vraiment le point spécial de ce doctorat. Ça n'aurait été pas la même chose avec un autre superviseur, je pense. Il a vraiment été capable de me laisser la liberté de faire de la recherche de manière indépendante et il a su me diriger, surtout quand la situation était un peu plus critique, peut-être, qu'on ne savait pas trop exactement où aller. Enfin, moi, je ne savais pas trop où aller. Et donc, vraiment, d'un point de vue humain, pour moi, c'était vraiment fondamental. Donc, je pense qu'il mérite vraiment un remerciement spécial. Merci, Alessandro. Merci beaucoup. Bon, j'espère n'avoir oublié personne, mais bon, je remercie vraiment tous les gens qui ont collaboré avec moi. C'était une expérience magnifique. Voilà, merci à tout le monde.
Bravo encore.
Félicitations.
Merci.
Oui, félicitations encore. On se revoit pour un champagne alors à Paris pour Noël.
Volontiers pour moi.
Il faut attendre que Macron nous donne la permission, mais et après, j'organiserai un pot, j'espère.
Pour l'aspect formel, s'il y a quelque chose à faire, il faut juste me demander si vous signez ou quoi que ce soit. Je ne suis pas au courant de la suite de la démarche. Donc,
je vous ai envoyé par mail, je crois à tout le monde, le fichier avec c'est le Word, le fichier Word qu'il faut remplir pour donner la délégation pour la signature. Donc je crois que tout le monde doit le remplir et l'envoyer à Sandrine. Et après,
Moi, je signe pour tous.
Oui.
Parfait.
Bon, bravo Marco.
Merci.
À bientôt.
À bientôt. Hein.
À bientôt.
Bonne santé à vous aussi.
Au revoir.
Ciao, ciao.
Et rentre bientôt.
La manip arrive là. Hein.
La manip arrive.
Ouais.
Il y a le devis ici que je vois.
On t'attend, hein, on a préparé ton bureau.
Ah, ok. Oui, non, mais je rentre. Hein.
Léo, il a déjà pris l'option, tu sais, c'est un peu tard là. Il est en Italie, il va pas le laisser partir.
Non, donnez-moi 10 jours et je reviens.
Très bien, on t'attend.
Allez, ciao.
À bientôt, merci.
Ciao.
Ciao.
Bye bye.
Ciao.
Bye.
Bye.